Sir, you are not audible, I guess.
Okay, sorry. Let me do it again. Yes. So now I'm audible.
Yes, sir.
Should be audible. Yes. So we had done this. Population is MA. J is the flux at the barrier top, and if I take a ratio of these two, I should get this. Okay. And you had this gamma by lambda and gamma by lambda plus gamma whole to the power half. And if you do this, you will see that you will get lambda by lambda plus gamma whole to the power half, this prefactor. You can check your calculation. Okay, so we had a problem here. I think I put gamma by mistake. It should be lambda divided by lambda plus gamma. Is this clear?
Yes, sir.
Okay, so now let us so now I have this. So this is what I have now. Okay. And then, so this is my expression for the rate constant. You can see the expression for the rate constant. So if I go back to your class notes, you will see in the class notes itself that, like, if you go a few slides back, you can check that your minus lambda was equal to A plus gamma. Can you check this? It should be somewhere here if I go back to the class note. Because when you defined this, it was like this. No. Where was that? Not here, not here. Can you check your class notes? Because it has to be there somewhere. I had defined this. Just go back to your class notes and you will find that it is there somewhere. Where did we define this? So let us go back. We had started somewhere here. Okay, we had this is flux over population, all these things like this. So lambda is a constant to be determined, you can see. And then here we have this relation. Can you see this? A plus gamma equals to minus lambda. All of you?
Yes, sir.
So essentially I'm using this relation. Okay, I'm using this relation. So go back. So minus lambda equal to A plus gamma. But you remember that which one should I take? Which A?
Negative.
Yes, the negative root we should take, isn't it? The negative root. So I can call it A minus, whatever. Okay. So I now go back to the next, go to the next slide. So we have lambda equals to, so what I have is minus A minus gamma. A should be minus this negative root. A minus means the negative root. So this is equal to, if I take the minus common, it is A negative plus gamma. What is the negative root? You can go and check your class notes. It was gamma. This gamma is there. What was A minus? A minus was, go and check, gamma by 2 minus root over gamma by 2 whole square plus omega b square, isn't it? I hope I'm not doing anything wrong. Just check your class notes. Should be this.
Yes, sir.
Okay, it's not a difficult thing to do. And then if I rearrange, what I'm going to get, I'm going to get this plus lambda by 2 and gamma by 2 and uh, minus, we have this minus gamma by 2. Okay, this is minus, there's a minus gamma plus of minus gamma by 2. So this gives you what? This gives you,
Gamma
you should get something like minus gamma by 2 plus and this is nothing but your a plus, isn't it, Anish?
Why did we do one? So the relation was mine. Okay, got it.
No, I think it's fine, I guess. Okay, I guess fine. So now if I take this ratio, lambda divided by lambda plus gamma, what will be the answer? Okay, lambda is a plus
Plus by a minus.
and lambda plus gamma means minus,
A minus.
like this, isn't it? This is how it is. So this one, I'm just writing it like this, minus, I just multiply with a plus in the numerator as well as a plus in the denominator. Okay, just writing like this. Okay, this is fine.
Yes.
Minus a plus into a plus means
A plus.
a plus into a plus, lambda square, of course, but you know what is a plus. A plus is this expression, no? So you have whole square. Okay, and what about this a minus into a plus? You know what is a minus, no? A minus is this into a plus. It is a plus b into a minus b kind of thing, isn't it? A square minus b square. So what I'm going to get, minus this one, no? A square minus b square. If you do it, it will be like this. So what I'm going to get, I'm going to get
Minus omega b square.
yeah, so this minus will also cancel, no? This minus and this minus. So it'll give you 1 by omega b square into minus. A lot of algebra actually. Okay, this is fine.
Yes.
So there's a final expression for the Kramers rate is k equals to, if I go back, I have whole to the power of half of this and then this factor, isn't it? So this factor, so let me write it down here. You have a factor like omega e by twice pi. Okay, and you are taking a root of this. This will give you root of omega b. Okay, I take this. This one, and then I have the exponential factor. So you have to. What is the exponential factor? Go back, vxb minus vxa, and let us write it as E. And this is, what is this? This is nothing but activation energy, no? You remember the diagram? I'll show you later. So this will give you okay. Are you convinced, all of you?
Yes.
Yes, sir.
So now we know for first order rate constant, rather, you can write something like a equals to a You know, this is this relation, this empirical relation.
RNA solution.
Yeah. So can you see the similarity between Arrhenius relation and the relation given by Kramers?
Yes, sir.
Yes, sir.
So actually, Kramers give you a very is a more general expression of the Arrhenius. We can compare. One can compare. You can see that it gives you expression of the prefactor, this A, in terms of the energy landscape parameters like omega A, omega B. So the potential energy parameter, also the friction. So they express A in terms of omega A, omega B, and friction. Okay. So now let us do one thing. If I now let me write down this expression again. The expression is this Kramers expression. This is something which is very important for physical chemistry and chemical physics. Okay. Okay, this is fine. Now, if I go to a limit where your friction goes to 0, low friction or 0 friction limit, small viscosity, what will happen to this expression? This gamma by 2 is 0, no? Taking
Yes.
0. Okay, so what is going to happen?
Omega A by 2
Omega
pi.
A by
Tell me, what is going to happen?
omega B will also go. Only omega A would be there.
Yeah, so what you are going to have? Going to have omega A. I hope everybody understands why twice pi. Because what is going to happen, this factor, this is small compared to this. So the expression inside the root over only omega B will survive. This will give you omega B, and then this is 0. This omega B will cancel. So it will give you omega A by twice pi. And do you know this expression? How many of you know this particular version of what is known as transition state theory? This is nothing but transition state theory result. How many of you know this? Okay. How many of you know this transition state rate? Because if you have energy landscape like this, then it escape over the barrier. No, this is your whatever the activation energy. E. This is omega A, omega B. You see that if I follow transition state rule, it will be K TST is given by the curvature of this frequency factor in the reactant well, which is omega A by twice pi means what? This is the frequency, no? Omega is the angular frequency divided by twice pi frequency times exponential to the power of E by kBT. This is nothing but your transition state result. Is this clear to all of you? And this is the actual transition state result expression. The one which is taught in thermodynamics, sorry, in statistical thermodynamics, that is using thermodynamic interpretation. So there the prefactor would have some temperature dependence and other things. You remember? So in that case, your E is free energy, you have entropy and enthalpy coming there. You remember that? That is Eyring version of transition state theory. So this is called Wigner version of transition state theory. Okay. So this one, KTST, is given by omega by twice pi. So what happens? So essentially, transition state theory result does not take into account or does not consider that there is a viscosity of the solvent or viscosity of the medium. Does not have that embedded in the theory, isn't it? In transition state theory, there is no notion of viscosity or friction, isn't it? So
Yes,
there is
sir.
no notion of dissipation, no dissipation in transition state theory. So no dissipation. So that is zero dissipation limit gives you transition state theory, and it is obvious then what will happen. Because transition state theory means once the particle reaches the barrier top, which is transition state in this case, one dimension. Okay. Once the particle reaches the barrier top, it is counted that the reaction has taken place, isn't it? So there is no recrossing in transition state theory. What is recrossing? Recrossing means I can have a trajectory like this. It goes like this and then come back. No such thing in transition state theory. But this exists in Kramers, because Kramers has the notion of friction. So the particle can go to the barrier top and even go a little farther and then can dissipate energy and come back to the reactant side. It can go to the other side also. It can also come back to the reactant side. Or it can take some energy from the environment and come back, climb up and come back. Okay, these things are in, actually it is there in your what is known as Kramers theory, and it is embedded here in this factor. So I can always write this as something like Kramers is something like transition state result times something like kappa. I can write it like this. Let us write it like this. So I can, the Kramers rate, I can write it as k TST into kappa. And kappa is called the transmission coefficient. What will the expression for kappa?
1 over omega b.
You know that because I have to leave out the transition state. So it is like this. Okay. So now it is also obvious the transition state result gives you an upper bound to the rate. Is it? Is it clear to all of you? Upper bound means the maximum possible rate. Maximum.
Yes.
Why? Because this transmission coefficient is
Bounded between 0 and 1.
yes, it is bounded between 0 and 1. Okay. You can just check this. So transition state theory result or the transition state rate is always higher than Kramers rate. Kramers rate is lower because it is actually for a chemical reaction or a physical process happening in liquid. You have a lot of dissipation. But in the gas phase reaction, the dissipation is so negligible that you can use this transition state result, and people use that. But in the condensed phase, in the liquid state, it is preferred to use. One should use something like Kramers. Is this clear? And especially for a mesoscopic system where people look at, for example, a biomolecule going from one state to other state, and that is also as if there is a reaction coordinate, and along that reaction coordinate there is some rearrangement in the biomolecule, and the biomolecule goes from one state to the other state. Okay. Even sometimes protein folding is also viewed as two-state folders, like there are two states of the protein can go from one to the other. There's a barrier. So in those cases, you can use something like Kramers rate constant, rate theory. Okay, Anish? And others, I hope others are there. Yes.
Sir,
Yes.
This theory cannot be applicable for pseudo first order reactions because there will be molecularity of 2.
See, Kramers theory is for actually what happens that this is for a rate process where the rate process is fast order. There is a fast order rate constant.
Only one molecule should be involved. There should not be concept like collision.
You can have more than one molecule, but there's one reaction coordinate. It is along one particular reaction coordinate. Okay.
Okay.
Sir, hello, sir.
Yes.
So when you see like the general case when the reaction like it goes back the hill, So for that, K should be negative. So how does this happen? Like, I guess,
K is not negative. Where is K? No,
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 no, it's not negative here.
no, no, no.
So
K cannot be negative. K cannot be negative. How can it be negative?
how will it go back? So it is like a
No,
backward
no,
type
no.
of thing.
It is not like K is something like average. K is average, no? It is, what is this? Flux over population. What is flux? What is it? Population? These are averages I showed you.
Yes, yes, sir.
And by definition, these are positive quantities.
Mhm.
So K cannot be negative. Do you agree? So
K
if you have recrossing, which basically means the value of K will be lower, but it cannot be negative. By definition, it is positive. It is rate.
Mhm.
Okay.
Okay.
It is okay. So now I can go to the other limit when gamma is large. When gamma is large, the gamma is much greater than omega b. This is called large viscosity limit. I can go to the large viscosity limit. And if I go to large viscosity limit, in that limit, my expression, let me write it down, omega a by twice pi was there, e to the power of minus e by kbt was there, and then I had this factor, I can call it transmission coefficient. What happens to that? What was that factor? This factor was minus gamma by 2. So let me write down the factor first. What was the factor? Minus gamma by 2 plus
Under root of.
okay. So in the limit, so this factor, let us concentrate.
Whole square by omega b, right?
And also you have omega b here. So 1 over omega b, you're right. So let's see what happens to this factor. 1 over omega b is here. Gamma by 2. So what I do, I just first you take gamma by 2 whole square out. Can I take this, like if I take gamma by 2 whole square out, what will have? What I will have inside? 1 plus omega b square into 4 by gamma square. Is this fine with all of you?
Gamma by 2 will come out, right?
Yeah, if I take gamma by 2, yes, sorry, gamma by 2. Yes. Okay. I should, like what I'm saying, that gamma by 2 whole square I take inside common and then take it out. You're right. So this will give me now I know that gamma is very large. So this is very small. So what will happen to this? This is going to be 1 plus half. This is fine.
Yes.
What will happen to this factor? Plus
So isn't root square
yeah.
whole,
What?
the minus gamma by 2 plus root gamma by 2 square plus omega b square, that whole thing is squared, right?
Which one?
The gamma dependent quantity of kappa.
This one. Yes. Anything wrong I did?
There is supposed to be a square outside the square bracket, if I'm not wrong. You just
Which one? This one.
the
Here.
quantity in square brackets, yes, the whole quantity in square brackets.
Whole quantity in the square bracket. Yes.
That there is supposed to be a square on it, whole square.
Here.
Yeah, if you would check the previous slide.
This is the one. Why?
Oh, okay. No.
Because I have this only the. I took this. No. We had lambda. Whole to the half was there. No.
Yes, I'm wrong. Yes, thank you.
So I don't think I have. So omega by, so this will cancel. 4 will cancel, gamma partially will cancel. You'll have omega b square by gamma. This will give you omega b by gamma. So what will be the expression? The expression is going to be okay. So that is, so the rate is inversely proportional to 1 over gamma, 1 over viscosity. Okay. So this is expected because as you increase the viscosity, your rate should decay. Sorry, should decrease, doesn't it? If I do
Yes.
reaction in two solvent, one solvent has a higher viscosity than the other. The solvent for which the viscosity is high should have the reaction rate should be smaller, isn't it? Slower reaction in high viscous liquid. So basically, if I plot this, say, if I plot this as a function of gamma k, what should I get? Something like this, isn't it?
Yes.
This is hand drawn. But in reality, you get this. Real plot. Where here it is 1 over gamma, but it is here, it is gamma. Okay. And I'm not going to discuss why, it is beyond the scope of this course. So far we have done this. So there are 3 regions. One, this is called high viscosity. Okay, the one we just did. Earlier we did this moderate to low to moderate friction, extremely low friction. Okay. And this part I'm not going to do. How, when you go to very, very low friction limit, why the rate is proportional to gamma. We are not going to do it. Okay. We'll just concentrate only this part we have done already. This is for the first part here. And this is for the next part, high viscosity. And this is a typical plot of the rate constant, Kramers rate. You can call it Kramers if you want. And this is called, actually you have a, first it increases and then decreases. So Kramers turnover. If you want to read this, more about this, there are articles. There's a review article by Peter Hange, 50 years after Kramers. Reviews of Modern Physics, 1990. And there's a person called Eli Polak who has done a lot of work. You can see his papers. But this is not important for this course. But if you're really interested, this is very, very, it's quite an advanced topic. And there is also quantum version of these Kramers. And if you want to know more about quantum mechanical version of these Kramers, it's called quantum Kramers problem. Then you look at the work by D.S. Rai, Cultivation of Science. Okay. So we'll stop here today because my plan, next class, what I'm going to do, I'll just recap for a few minutes maybe. In the next class, What I'm going to do, I'm just going to recap everything. So the next class, when you come after reading everything on Brownian motion, okay? And then you can ask me question. We will discuss. The whole class will be discussion of Brownian motion, starting from my first class on Brownian motion till Kramers rate. And I'll show you some example of Kramers problem in the next class. Is this clear to all of you?
Yes, sir.
Yes. And how many classes are left? After that also we have one more class, I guess, on 19th, isn't it?
Yes, next one.
But next Friday is not there, no? The class is not there, no? Not this Friday, and so not this Thursday. Next Thursday, do we have a class? I don't think so. There is some, as far as I remember, that class is not there. But I don't know. I don't remember why. Can you check and tell me?
एनसेम का सिलेबस पूछ कोई
Excuse me.
एनसेम का सिलेबस पूछो कोई एनसेम का सिलेबस पूछो
Who is this guy? NSEM syllabus is everything. Whatever you have taught from the very first day.
Yes, according to the calendar, the last date of instruction is 20th April.
Yeah, so 20th, no? So today is 12. So 12 and then I have on 15th, no?
Yes.
And then I should have one more class on 19th.
Yes.
Yes, so that's what I'm saying. So yeah, after today, I have two more classes. So these two classes are dedicated to discussion. So next class we'll discuss Brownian motion, other things, and the rest, Ising model and other things we'll discuss in the next to next class. We'll just discuss only the class notes. Is this clear to all of you?
Yes, sir.
Okay, so you read Brownian motion, you read, and come to the next class, because I don't want to stretch it further, because I wanted to do linear response, but we'll not do this time, because we have already done a lot of stuff. It's quite heavy. So next two classes, and I'm leaving early today. So next two classes will be dedicated to brushing up what I have been teaching you in the last few classes after mid-sem. So the final exam will be heavily on the syllabus after mid-sem, but some parts, little bit, will come also from the part which I taught before mid-sem. Is this clear to all of you?
Yes, sir.
So maybe 30% will come from the part which was taught before the mid-sem, and whoever was asking this, ask what is the syllabus. So he is listening, I hope. And also after the mid-sem, that part would carry something like 70%. It could be 80, could be 65. Ballpark number is 70, 30, 70. Is this clear to all of you? Okay?
Yes.
And please go through my notes, and I have sent you the notes by DS Ray. Go through that note as well. But that note has a lot of typos. I hope you have realized. I don't know whether you have gone through. If you go through, you'll see there are typos which I have fixed when I taught you. Okay, and one thing you do, all of you go to Google and give search Kramers rate in chemistry and biophysics. A lot of application in biophysics involving biomolecules. Okay, that'll be interesting to see what are the application of this Kramers rate. Okay, we'll discuss in the next class. So we'll stop here today. We had a very small, short class, but that's okay because we had so many classes, and the last class was pretty long. So we'll stop here, and I'm stop presenting and stop sharing.
Sir,
Yes.
sir, will this Kramer rule will be applicable for process like electronic transition singlet to triplet state?
How can you apply? That is quantum mechanical. This is classical.
Yeah.
If you have a quantum version of Kramers, which I did not discuss, that is used in many other contexts where you have quantum mechanics. This is classical. Okay.
Sir.
Okay, I'll stop. Yeah, Nashit.
Sir, we have not touched upon the non-equilibrium part, right? we are still in the near equilibrium regime. In the
Because this course is not on non-equilibrium. It is on, it is, you can call it non-equilibrium, but in strictly speaking, it is very close to near equilibrium. It is close to
so
equilibrium.
so when we do stat mech in non-equilibrium,
Yes.
so what is the things that like some
Then you
things
don't have fluctuation dissipation theorem. So, and then there is no standard framework. Actually, it is evolving area, and it is a lot of activities, research activities in that area. Okay. You can, if you get a chance, you can visit my lab later. I can show you what are the things we do and others are doing. Okay,
Sure,
so
sir.
that is quite advanced, and this is beyond the scope of this course. That is beyond the scope of this course. Okay,
Yes.
so we'll stop recording and we'll see you on Thursday. But you know, this Thursday and next Monday, we can discuss the little application of Kramers, but we will brush up whatever being taught after the midsem. Okay. Yeah.
Okay,
So,
sir. Thank you, sir.
yeah, I'll stop recording. Yes, thank you.